Today we're going to be presenting our 4th episode of our Graph Gurus series. Today we are doing part 2 of our Detecting Fraud and Money Laundering in Real-Time presentation. And there's a few housekeeping items before we get started today. Go to the next slide. So everyone is muted, so we would ask that if you have any questions regarding the presentation, that you use the Q&A feature in Zoom. And if you have any questions directly for us, my name is Emily, by the way. If you want to chat with me directly, if you have any technical issues, you can use the chat function. And so at the end of the presentation, we will have a 10-minute Q&A. And during that time, you can send questions to us using that Zoom Q&A tab. And we are recording the webinar, and we'll go ahead and send that to you at the end of the day today. So we're going to go ahead and get started and introduce our moderator today.
Thanks a lot, Emily. Hi, this is Gaurav Deshpande. Some of you have heard from me before. Those of you who haven't, welcome to Graph Gurus episode 4. A little bit of a background about me. I have about 22 years in supply chain management, big data and analytics, built out IT technologies, supply chain management and analytics portfolio, took it to IPO, followed that up with a master data management company focused on managing product and customer information that was acquired by IBM. As a part of IBM, I built out IBM's big data analytics portfolio, about roughly $4 billion per year portfolio. Grew that about 45% year over year for about 7.5 years before coming on over to work with the most exciting startup I've worked till date, which is TigerGraph. For 14 patents in supply chain management and big data analytics, and I'm excited to share details about money laundering with you. This issue is personally very close to my heart. Because it's the size of the issue itself is massive. I'm excited also to present with me, after I do the initial introduction to the business problem, Dr. Dan Hu. Those of you who attended last couple of weeks back, the episode 3, will remember Dan is a quantum physicist. He has a PhD in quantum physics. He is our top architect and developer, and he specifically worked on solving this money laundering problem for one of our largest customers. So he's going to be sharing that with you, and he's going to show you how you don't have to be a quantum physicist or a PhD to detect money laundering. It's going to be literally in half an hour. You will be an expert at finding one type of money laundering, and we will give you more information to detect other types of money laundering in a follow-on episode. Let's go ahead and go to the next chart. Money laundering is an interesting problem, and it's one of the ones that is biggest in size in terms of a problem. Fraud is about $100 billion or more estimated. The size of the money laundering is estimated to be right between $2.5 to $3 trillion. I'll repeat that. The size of the money laundering problem estimated is about, that's a conservative estimate, but between $2.5 to $3 trillion is 2 to 5% of global GDP, gross domestic product. Even more importantly, though, money laundering is what is used by drug traffickers, by terrorists, to fund their activities. So not only is it a matter of financial importance, it's a matter of national security for all of us and security for each of our households. So that's the reason why it's exciting for me to see TigerGraph solving this really, really difficult problem. A typical money laundering scheme would involve many accounts. What money launderers tend to do as they get more and more sophisticated is that they create synthetic identities. They will take a valid social security number in the United States, or a national ID number in China, or a UK national ID number, and take a combination of that with valid address, valid information, and then create synthetic identities with multiple accounts and route that money through multiple accounts. In some cases, that money ends up back into the same account where it started, while it goes through literally tens of different accounts. while another type of money laundering, which is called layering, where you'll actually, structuring, you'll actually distribute it, a large quantity, into smaller amounts, and it keeps on filtering through the financial network to reach a handful of accounts at the end. And typically these accounts are owned by the same person or same cartel or same terrorist organization that started the initial money transfer. What they are doing essentially is taking ill-gotten gains, whether it's from drug trafficking or activities for funding terrorist organizations, taking those from one part of the financial network and distributing that through multiple accounts and having it show up as legitimate money at the other end. So that's what money laundering is. You can go to the next chart. In terms of techniques, I talked a little bit about that. Layering or structuring is a technique. Both the terms are used where you split it. You take $1 million, for example, split it into small quantities like $2,000, $5,000, $6,000. Typically, in terms of rules, the tracking, financial transaction tracking, one threshold is $10,000. So anything that's below $10,000 is not actively tracked. They make use of that loophole with United States and European Union to essentially structure those payments into smaller accounts. So what you see at the top is red account is the one that owns the money that has, let's say, $1 million. They'll break it literally into hundreds of the orange accounts and the purple accounts and multiple layers of those. And here we have shown you a simple structure that has 4 layers. This can go up to 11 or 12 layer structure. So we have seen this fairly complicated as a part of our customer base. And this is an inherently graph problem because, as you can see, that money is flowing through multiple outlets, and it looks like a graph because it is a graph. That's the reason why it's a perfect fit for graph analytics, and especially very good fit for TigerGraph because we are a massively parallel processing system. So we run, as you can see, just the way a processor threads run along multiple threads and then come together. The money laundering financial transaction scheme looks very similar. So we are able to do that by utilizing our massively parallel processing, or MPP, technologies that we have built on. Let's go to the next chart. Layering loop has a lot of different transactions. Of course, one of the popular ways that people do layering is that they will have money broken up into multiple accounts, and then they will pass it on to more accounts. They go through more layers, and then eventually that loops back into the same account where it started. So that's called a layering loop. Today we're going to show you that example of a layering loop that can have as many as 20 different hops, and we can show you how TigerGraph processes that information. We're going to show you the GSQL scripts related to that. With that, let's go to the next chart. Here I'm going to talk a little bit about the workflow with TigerGraph and machine learning. The key thing to understand is very simple. You know that there are certain types of patterns that you have seen from money laundering. Your machine learning tool system has detected that no matter which tool do you use, whether you use TensorFlow, you use R or Python libraries, or you have your own machine learning libraries, ultimately you're finding a set of patterns. And based on those patterns, you have a certain set of graph computed attributes that you have figured out. Those rules or those patterns are then baked into TigerGraph as graph analytics computation. And that generates the initial set of features for the machine learning. So that feeds into the machine learning. In addition to that, machine learning will also figure out over a period of time patterns that are not yet detected. So they will find new patterns that look like money laundering patterns. Those in turn will get converted and codified into the TigerGraph real-time operational graph database, and we are able to, in real time, enforce those rules again, create more information, more training data, and detect money laundering loops in real time while they are occurring. So that's very important because typically in a money laundering cycle, you have 24 to 48 hours after the transactions are completed to do something about it. Otherwise, the money by then has been siphoned off to completely different accounts and you're not able to track it anymore. So the fact that we do this in real time is a game changer for majority of the financial corporations that we work with. And more importantly, it keeps tracking the dirty money, flagging it, and helps us reduce funding for terrorist organizations and drug cartels. So with that, let me hand it off to Dr. Dan Hu.
Okay, hello everyone. So today I will talk about the anti-monitoring with TigerGraph. So it's specifically on the layering loop detections. So anti-money laundering. So if you want to build an effective anti-money laundering system, at least you need to fulfill the following two features. First, you have to detect all suspicious behavior quickly. So system should find all suspicious patterns or wrongdoing at all times. So that means that you need a real-time system to find those suspicious behavior. Another feature you need to have is be easy to use and change, because all patterns can be easily applied, need to be easily applied, and user could easily modify the pattern to adapt new rules, because those patterns change accordingly. You have rules, and those money laundering patterns, they might change accordingly. So you, on your side, on the money laundering side, you also need have tools like can easily model your previous pattern to adapt the new patterns. So that's why TigerGraph can help you in this to build such an effective anti-money laundering system. So why you want to use TigerGraph? So TigerGraph is a native graph database with multiple built-in graph analytic tools. So we have the shortest paths, built-in the shortest paths, all paths, those built-in algorithms. And you can use to find some regular patterns. And also we have a GSQL language. It's a powerful graph query language. It can do the graph traversal and aggregation at the same time, also running in real-time fashion. And you can think like detection of suspicious behavior can be always converted into a graph pattern matching problem. And because it's a graph pattern matching, our GSQL language is a good fit for this type of problem. So let's look at some examples. So examples like you can use a graph database system to detect one level frequent money sender and receiver. It's basically one-step neighbor traversal. Another thing is you detect the two layers of frequent money sender and receiver. It's also like a two-step neighbor traversal. So those two jobs can be easily handled by most of our current graph database like Neo4j or Neptune. But what we are focused today is the last one, like the detection of accounts with loop money transactions. So we want to detect loops among those transactions. So with the following constraint. So we must have a controllable search depths. So the search depths could be as large as possible, like up to 20 hops. It's not like one step or two-step neighbor traversal. It might be multiple hops. That's very common when you detect the loops. And also, we need a time window. We give a limit time window. We want to look at for this time window, what's whether there's loop transaction or not. So we must give a time window as a restriction. Another is you can limit the money involved. Give a lower limit on the money in this loop. And another thing is a drain ratio. Drain ratio is defined as the maximal money amount involved in this loop minus minimal money amount involved and divided by maximal, so that it's give the percentage like how the money fluctuate along your loop. So that when you do the loop detection, you don't want like the money is like have a very large fluctuations. And also another requirement is you want your loop is actually all the transaction in loop in a forward time series, so that every transaction happens one after another, so that it's really a money laundering loop. So with all those constraints, actually TigerGraph can provide you a way to detect those loops. So in order to address this problem, let's look at the graph schema we have. So in order with those restrictions, we built such a graph system, such graph schema. So we have a account. So on the account, it's just basically to represent the real account, and we use some flags on this account to record what type of account it is, what type money laundering it has involved. Another is a transaction node. So the transaction node is just record a transaction event, because in the last episode we don't use event nodes in the phone fraud, because phone fraud we are not care about transaction detail, but in here we actually care about each transaction. So in this loop detection, we actually store the transaction as an event node. Another thing, one-day node is actually a time index node. That's how we build an index for our database. So that this time index node is connected with transaction nodes. So we can fulfill the time window restriction. So we only look at transactions within a time window. How we do it? We just build this time index nodes. Then we build a directed edge. It is called send edge. It's actually follow the money flow. So account start a transaction, it has a send edge, and it's go to another account, it's had another send edge. So it's a direction edge. So we have a directed edge. And because in the following we are talking about how implement our algorithm, actually we requires a reverse edge. So that's why we build a schema. We have this send has a reverse edge called reverse send edge. Each time you have a send edge, our system will automatically build a reverse send edge, so that in this way, if you receiving money from some transactions, you actually have an outgoing edge represent this event. Okay, so that's our basic schema. We are going to implement our algorithm based on this graph schema and using our GSQL Query language. So let's talk about the algorithm. So loop detection. So the most easy way or the brute force solution would be start from the account you want to check and just do the graph traversal. Just do the graph traversal using only the send and follow the send and check whether within the maximum number of steps you can go back to your original account. Then if you can, you find a loop. If you can't, this is not a loop. It's not a loop transactions. But this algorithm actually has multiple disadvantages. First, it's memory cost. It has very high memory cost because you need to record your paths while you are traversal. So for those paths that never form a loop, you also need to record those passes. And from the previous picture, graph shows, you know that there's multiple layers. If you go multiple steps, actually it's spread out a lot of notices. So if you do this algorithm, you actually collect a lot of passes, unnecessary passes, because those are never being a loop. Another thing is computational cost. Because you are going those loops, you cannot stop early. You just stop until you arrive at the maximum number of steps. So that's another cost. So that's why in our implementation, we didn't use this brute force solution. So we actually use a so-called bidirectional loop detection. So in a bidirectional loop, so we have 3 phases. So the first phase, actually we use a bidirectional search, but we are not building the path while traversal. We don't build the path in the first phase. We just mark the subgraph. So basically, we traverse from both forward edge, that's the send edge, and also the backward edge, the reverse send edge. We go through those nodes and we mark. If it's a forward reachable node, we mark it forward reachable. If it's a backward reachable node, we mark it backward reachable. And we just mark those nodes, and then we use the bidirectional search to find out all the valid vertices that are in one loop. Then we mark it as our subgraph. That's the phase 1. We don't do anything about the path. We just mark the subgraph. Then in phase 2, what we do is we retraverse the graph, but in this time, we limit ourselves into the subgraphs. We only traverse the subgraph notice, which was marked by the first phase. It has a flag, this is a valid vertex. We only go to those vertices. So because those vertices are all in loops, then we just collect, while our traversal, we collect the paths. We collect the paths, use a list to record all the paths we traverse. Then we can apply some path-related filters. In phase 3, some path filter like the drain ratio. You know, the drain ratio is the maximum money, the money difference of the loop divided by the maximum money. So those filters are path related, is for each path. So it's easier we implement this type of path filters after we get all the loops and we filter out those invalid paths, and the result are the paths we return. So that's our 3-phase algorithm to solve this loop detection. So actually in here, the start nodes, you can think about it as a single account, or it's actually multiple related accounts, such as those accounts are linked by the same ID, we treat them as the same account. Then this algorithm also applied to this case, like with multiple linked IDs, we just do one-step traversal, we mark them, this is just our start accounts. So we still do the loop detection. So that means that this algorithm applied to the multiple related accounts. Okay, let's look at details for each phase. So for phase 1, as we talked about, we want to mark the subgraph for all the potential loops. So our algorithm, actually we separate into 2 parts. One part is we traverse the first half of the node, half of hops from starting account. We label vertices with forward and backward reachable flags. If it's touched by the send edge, we mark it as forward reachable. If it's touched by the reverse send edge, we mark it as a backward reachable. So then for the second half of traversal, we actually do not go to other nodes. We only traverse among the vertices with assigned reachable flags. So the rule is forward reachable vertex can only reach backward reachable notice, and the backward reachable vertex can only reach forward reachable vertices. So in this way, we are actually limited our traversals only for potential loops. The first half of the traversal is just mark all the forward and backward reachable, but another half traversal, we just go to only the loop candidates. Then all the potential loop candidates are the vertices with both forward and backward reach flags. So that's the algorithm we are using for the bidirectional search. So let's look at step by step. So bidirectional search. For example, the first half, as we said, is actually just do the marking. So we start from the first, the starting account, and we label its neighbors. So if its neighbor is connected by a sender edge, we label it as green, means it's a forward reachable vertex. And the reverse edge, we mark as blue, is a backward reachable flag. We continue, this is our first iteration, continue to our second iteration is from the transaction to the account. Then we do the same thing, it's because this transaction is forward reachable, so we label its neighbor as forward reachable and throw the sender edge. If it's a reverse reachable, go through the reverse reverse edge, we go to its neighbor, mark as green, as blue, as a backward reachable. Then when we arrive at the middle points, so you will find that this transaction would be marked by both vertices. It's both forward and backward reachable. So we mark as red, indicate that it's a valid vertex for our loop. And in the above transaction, we arrive at T5, it's only forward reachable. So starting from this middle point, the transaction and the traversal changed. That's the second step. So for here, we know for the next traversal, we know that T5 is a forward reachable, so that it can only reach to vertices like it's backward reachable. So from here, you see that this path will be skipped because it doesn't have any label like with a reverse labeled vertex. So that we stop this traversal early. We just, by half of the traversal, we just stop there. That's how we stop early, how we reduce the computation cost. And look at here, the T3 previously is both forward and backward reachable. So it continues goes to the forward edge, the send edge to A3, the account, and it mark it as forward reachable. So the A3 become another valid vertex. We mark as red. And also T3 can also go through the reverse send edge to A2, so that it mark A2 as a valid vertex. In this way, we can actually mark all the valid vertex along the loop until we go back, the last iteration, we go back to A1. In this way, we have a subgraph with all the valid vertices marked as red. That means both forward and backward reachable. So in this way, that's how we find out the subgraph. Right now, we haven't built the path yet. It's just for the label each vertex. Then let's come to our second phase. Our second phase is actually to go through this subgraph again, but we limited our traversals only to the valid vertex. That's those vertices marked as red. And in this traversal, we actually do two things. One, we build the path for each loop. Previously, we only marked vertices, but here we actually collect those vertices along the path. And also in this traversal, we only go through the send edge because that's the money direction. We only go through the send edge, the forward edge. We only go to the forward edge, and we only go through the vertices with red marked. And actually, during the traversal, we also apply filters on the transactions with the forward timestamps. We don't go to the transactions with like a timestamp. This happens earlier. This must happen later. But if the transactions is not in a forward timestamp way, we need to stop the path collection. So TigerGraph achieves by collecting the timestamp on the transaction node and send it out into the account nodes. And during the traversal of this account to the next node, they know that which targets is valid. We only look at the transaction that is larger than the previous transaction. The timestamp is larger than the previous transaction. That's how we apply the transaction forward timestamp filters. In this way, we can all collect passes into a path with time increasing transactions. So let's look at this each step by step. So iteration 1, we through the send edge. It only transaction 2 is marked as red, so we go through this step. We continue, we move. We form a loop. While we form a loop, we use a list to record all the paths, all the nodes along this path, so that we have a list to record each path for the loops. So that's our phase 2. Phase 2 actually just build the path for each loop, and we apply the transaction, we apply the filter of the transaction with forward timestamps. Okay, phase 3. So far we collect the passes with the forward timestamps, but we haven't applied the drain ratio filter yet. The drain ratio talking about the money involved for each pass must be within some percentage change. So in this way, phase 3, we only apply this filter because we already have those passes. We use our UDF functions to apply these filters on each pass, go through each pass and try to find out whether they fulfill this condition or not. If it's fulfilled, we let it's a valid pass. If not, it's invalid pass. So that's basically the three phases of our loop detection queries. So let's look at, now we are going to look at the GSQL queries, how I implement this. And also let's first look at the data we have here. So for today's demo, we use a graph with, look at the graph statics here. We use 9 million vertices with 27 million edges. So for each type, for example, the date index node, we have 83. That means that it involves 83 days of data. And it has a transaction of 4 million transactions within 83 days. And also it involves 4 million accounts for those transactions. And the edge, the sender edge has 9 million. The reverse sender edge is the same number. And the one-day transaction is the same number as the transaction. Okay, so that's our data. Let's look at the query. The query, as in query here. Okay. So this is the GSQL implementation of the loop detection, or we call here circle detection. So it target at try to look at one single account, whether it has a loop, or not. So it gives the filters like what's the minimum step you want to go, and what's the maximum step you want to go. Remember here, these steps are actually double all the hops. It's actually because in our graph schema, we from one transaction to one account to another account actually goes to 2 hops, one to the transaction node and transaction node to account. So here actually, if the higher limit, if the default value is 10, that means that we go to 20 hops. But actually, when you run a query, you can give any limit as you want. But we just, for this query, the default value, if you don't give this parameter, the default value is we first, at least we travel 6. We need to look at loops larger or equal to 6 hops and to maximum 20 hops. And also, we have parameter to control the time window. So it gives the start time and it gives end time. And also we gave the limit on what's the lowest money amount you want to look at the transaction. So we don't look at transaction with any money. We only look at transaction larger than this given money. And also we gave a drain ratio as input parameters, so that we tells you what's the percentage of the transaction you want to do. So that's the input parameters for the circuit detection. So for here, I think if you learn some basic for the GSQL, you will know that we first define some accumulators for our graph traversal. Those accumulators are, if it's a local accumulator, it's one at. That means that these are created for on each vertex. If it's a double at, that means global accumulator. That means we use them to some global variables to control our workflow. So for here, we use it first on line 3 and 4. We actually use 2 flags, means that to record the minimal distance to the source vertex. We left distance, right distance. In this way, we can find out the valid vertex. So and also we use a flag like it's valid to record whether it's a valid vertex in the traversal or not. And we use some accum to record the transactions, the total transactions involved. And also we use some edge list accum to record the edges. So that's the basic information we want to collect during our traversal. So our edge tuple defined on line 2 is actually record the edge, the vertex of the edge, and the amount and the date, because the amount and the date are useful for the low limit filtering and the drain ratio filters. So we need to collect those 2 informations while we are building the edge. So let's look at the workflow here. So here, because we mentioned we want to start from our input vertex and do the traversal. So we are given the the time window. For the first block here, we use a edge block. We want to look at how many transactions this seed has been involved. But look at here, the line 33. We go through edges, not only any edge connecting with this account, not only the send edge, but also the reverse send edge. Because we want to look at all transactions this node has been involved. So in this way, what do we want to do? We want actually to give a more detailed time window. You give the input parameter gave me a time window, but actually all the transaction this source target involved has timestamp. If we look at those timestamp, we actually know a more detailed time window. So that in this way we can limit it. In our graph traversal, we can limit all the transactions must be in this limited time frame. So that's why we have this block here. In this block, we actually collect the information of the mean source send time and the maximal source receiving time. So that means that all transactions starting from these nodes, they must be bigger than this timestamp. Or else all your transactions is happening before this timestamp is not important. Because in the loops, other vertices will have other transactions. We don't care about those transactions. We only care about the transaction like form a loop for the source. So we have a mean source send time, and also for the same thing for the maximal receive time. So when you do the backward search, you want to know that all the transactions on this node must be smaller than this times, because in this way we can make sure that all the loops it involves is actually in a time forward series. So we just in the accum block we collect those two information, and in the post accum actually is on the source because we collect the source. So we go back to the starting account. In there we just initialize some flags for this source vertex. So we mark the distance to the source as 0, and we also mark this vertex as a true vertex. So for here, we add a having statement. For here, if the maximal receive time is bigger or equal to the minimal send time, that means that this account is not possible to have any loops with forward time in the forward time series, because your receive time is already large on all your sending time. So in this way, we can immediately skip for this input vertex. We don't do any traversal because you never will find a loop. So that's our first block. Then this following block is actually for the phase 1. Phase 1 is we mark the subgraph. So we mark the subgraph as we talk about in our algorithms. We actually separate it into 2 steps. First step, we go through the half of the maximum loops. We go through the half and we mark each forward reachable and the backward reachable vertices. So look at here, we just start from, we have 2 vertex sets, both actually seed, because in here, I intentionally separate our traversal into the forward search and the backward search, so that the code looks more clear, more readable. So first, we look at the forward search. We start from a seed and we go to the seed, send add, and we arrive at our transaction node. So for here, I have some where conditions. Those are actually used to filter out those transactions are not in the time window, and the distance that we want to all the transactions are first visited, so that the mean left distance is actually untouched, it's unlabeled vertices. So in this way, in the accum, we just mark it as left visited by citing the distance to the source, the mean left distance. And in the post accum, we just continue to apply our time our distance requirement that if both are really plus together smaller than the 2 steps limit, then this is a valid vertex. It's basically equal to say that if it's both forward reachable and the backward reachable, then this vertex is a valid vertex. So we mark here because during your traversal, you might have found some vertices it's already both reached. So we just mark it. Then from transaction, it's still forward search. We start from transaction nodes because right now X is already selected as target. So right now X actually a set or transaction. So from transaction so then to the account, we still apply the similar filterings, and we just find out whether this target is valid or not. Then that's for the forward search. Then for the backward search, we start from Y. Y is a vertex set with C initially. And then we go to a backward edge and we do those filterings and we mark the vertices. And the same thing from transaction to the account. So that's actually finished two hops search for one transaction from account to account. So at the end, we update our steps because that's only one step, 2 hops. Then it's a health statement. So it's a health statement. That means that when we go back to the line 71, it's a health statement until you arrive at the half steps. So let's actually do our labeling. So we propagate our labels forward reachable and backward reachable to every nodes we met. And if it's both reachable, we just mark this vertex as a valid vertex. So that's our phase 1. The step 1 of phase 1. Step 2 is actually another half or search. So we still require this do a while loop, but the step must just smaller than the high limit. So the same thing, but in this way, we actually had more conditions. So we have the condition or amount low limit, we have time constraint, and also we want the source target and left distance. Okay, look at it here. We still go to the forward search edge. We update it, use the forward flag to update the distance. And the same thing, if it's both reachable, that means that this is a valid vertex. So we do the same thing as from transaction to the account. So do the same thing. And then we do the reverse search, do the same thing, do the mark. That's the end of the phase 1. At the end of phase 1, we will have subgraph. We'll have all vertices, if valid, is labeled as valid. Then our second traversal. Our second traversal is target look at to collect the passes. So we just limited our traversal as the step high limit. We don't separate it into 2. We just separate it into 1. And we only go through the sender edge because in this way we are building the path, so it has a direction. We only go through the sender edge, and while the traversal, we actually build our list of the edge. We build we collect the information while we are going through, and for each path in your path list, we actually make sure that the timestamp is later than the previous timestamp, so that in this way, only when it's fulfilled, we add it into our passes. So that means that in this way, when we collect passes, it's actually built a path with the time increasing way pattern, that is forward timing steps. So it's just some marks, and the same thing from transaction to account. So that's a lot of detail. You can read it later, but basically we are collecting the passes and also apply the filters on the transaction time. Then at line 313, we have a UDF function. As we said, our phase 3 is actually to apply the drain ratio check. The drain ratio check, we did it because right now we already collect all the valid edges into a global variable called circle edge tuples. So we just use a UDF functions to apply this drain ratio check. So basically this UDF, what it did is go through every list. It's a valid path. We go through every path, we check the money on each transaction, and we make sure that this path doesn't have the drain ratio bigger than this value. So once after this UDF, they will automatically modify this global variable. All the edges into this circle edge tuple would be the valid path, fulfill all the filters. So that's the query. That's a query for a single account, how to find out the loops for this query in G-Circle. So yeah, that's basically our queries. And now let's go back to our slides. So another thing we haven't discussed so far is right now we only give a query for a single account, but usually people care about like all the possible accounts with loop transaction. We want to find out those accounts with loop. So it's batch processing. So in order to do batch processing, usually way is we make some changes to our algorithms. We make sure that we do not write query for a single point. We give a multiple input so that each time we just run the query for multiple inputs. But according to our experience, actually, first, if you start from multiple vertices, your algorithm would be complicated, very complicated, because when you record the path, you are not recording a path for a single start point. You need to record path for multiple vertices. So that means that you need a map queue, at least a map queue, to record that which path this belongs to. This actually completes your algorithms. And they actually, because all those additional accumulators, complex accumulators, they may actually reduce your performance. Actually, that's from our own experience when we deal with like single query and multiple query. So for G-Circle, we actually have an alternative way to speed up the batch processing. So we call it the query calling query feature. So let's look at what's that. So we actually use query calling query in parallel inside of the G-Circle. In this way, you write a subquery, it's only for one single vertex, but actually you can use our vertex block or edge block to run those subqueries in parallel. So it's automatically parallel. That's how we deal with batch processing in G-Circle. So for example, for the vertex block, you start a vertex block with all the candidate vertices. And in the accum, you just call your subquery, your loop detection subquery. The accum block, you know that if you are familiar with G-Circle query, you know accum block is executed for each vertex in parallel. So this actually makes loop detection for each vertex in parallel. Another way is we use our edge block. It's actually the way we did in this project. So we don't start vertex block, we start edge block. Because in this project, we have a time window for the transaction nodes. So the transaction nodes is connected with accounts. So it connected by edges. So it's a naturally fit for the edge block. Then we just call the loop detection for the target. The target is our candidate account vertices within the post-accum block, because post-accum is also executed in parallel for each vertex in the post-accum. Post-accum is on the target vertex, is actually on the account vertices. So we call the subquery in the post-accum to make it parallel, running in parallel. So let's look at the query again. So the query batch circuit detection. So the query is pretty simple. It just gives you a limit, the step load, step start time, end time is the same thing, just the same thing. Then look at the different points. That's where we use our time index node. So if you give me a time window, I first start from all the time index nodes and find out that the index nodes, the date site is actually the index valid index nodes inside this time window. And then the print is actually for the debug purpose. We put it here. We don't need it. Then we find out all the transaction site, all the transactions, because the time window, the time nodes, the index node is connected with transaction. In this way, we find out all the transactions, just one step travel to find out all the potential transactions. We need to look at it. We need to check whether those transactions are in the or not, in the time window or not. Then what we did is, as we told you, we use an edge block. We from transaction to the account. And in the post queue, we actually call the previous query, the circle detection query. We gave the target, we gave the account ID, we gave pass the parameters, and we collect the information into the into a local accumulator called the circle pass. That's the pass all the filters. And in this way, we do the check for all the transactions, for all the valid accounts within the given time window. And that's how we do the batch query. So that's actually our batch processing queries. So now let's do a live demo to run this query to see what's the result we have. So the output, actually, we don't need it. We can keep it as a default. It's just for the log purpose. So the money low limit, we can input like a 10K. The drain ratio, we can have a drain. I actually run this before. Let me record look at the. So this is a query we write in the command line. It's actually, we can write in the UI. So it gives a parameter. That's how we write. So the parameter is here. We just borrow the parameters here. So let's go back here. So the low limit is 10K. The drain ratio is 0.4. 0.4. The step low is 3, or we use default ones. The start time, so it's actually 2016, 05, and 12. Ending time is 2016, 05, it's 21. So for 10 days, we just look at 10 days and we see whether our parameters are correct. The start time is this one, because this is the one we find out the loop transaction, the parameter, we find out the loop transaction. So it's for running for 10 days and the maximum 20 hops, minimal 6 hops. So the okay, let's run the query. So actually this one will run like 18 seconds because it's actually looking at all transactions within 10 days. So that's why this one running so long. You can wait a little bit and see the return results. Check. Okay, we can see the that's me. Okay, those, let me see. Okay, so those are the loops we found within 10 days. Now it shows the, let me make it more clear for us to say it's citing. So for account, we just show type. For transactions, we can show the date time. So, okay, so look at here. So those are counts. Find the loops. Our starting loop, you can see the transaction. The transaction is actually, you can say it's 5th, 20th, it's 14. It's actually 2 p.m. Let's say it's 10 a.m. So this is our starting nodes. It's at May 15, May 15 is start a transaction, and the transaction has a 10,000. I think it's 100K. Start a 100K transaction to this account, and then 5 days later, it has another transaction with 82K. So it's within our drain ratio and to another account, and at a later afternoon, it gives another account like 70K and go back to the original account. So that's our query result. We can show it using this UI. So that actually shows that we found this loop within these 10 days limit. So yeah, I think that's end all my presentation. Emily.
Okay, yeah, so if you have any questions, we don't have a lot of time left today, but if you have any questions, we do have a couple here, but now's the time to send them in via the Q&A feature in Zoom. So we have one question: what are the pros and cons between the rule-based anti-money laundering and the way TigerGraph does anti-money laundering?
Well, do you want to address that? Yeah. So actually, the rule-based means that you actually find some rules. So if you find some rules, you want to make it more efficient, because when you find rules, you must look at other features as well, so that if you collect those infos, you actually spend a lot of time. So rule-based, once you find that this is a very useful rule, so our GSQL query language can help you to actually implement this rule in a more efficient way. So that it makes we have the REST call, not only from UI, we have the REST call, so that you can check through very quickly, make it in real time. So let's TigerGraph use the rule. Another thing is actually our rule-based can be a feature of your machine learning. So you'll find, for example, if you're in your machine learning, you use whether it has loops as one feature. We just use this query to find this feature, to check whether this vertex has a loop or not, to provide a result for one of the feature as one of the feature. So in this way, you can also do the machine learning just with this gquery to write the execution for this feature. Yeah.
Okay, so I think you just answered the other question. So let's see.
I see one more question here. The question is, what's the biggest scale of money laundering that you have deployed in production? Money laundering tends to come in different forms and different sizes. The largest one we have deployed till date that we have in production is at Alipay, Alibaba's payment network. There we have as you will remember in Graph database, every node, every payment, for example, every credit card, every account becomes a node. We are in production with over 100 billion nodes. We are in production with nearly 1 trillion relationships. And we handle about 100,000 transactions per second, rating each payment transactions for both fraud and money laundering. So that's the biggest one. But we have all shapes and sizes in our customer base, from that all the way down to tiny fintechs. We support everybody, and we do it with better cost of ownership than anybody else in the market because of our performance.
So we're out of time now, so if you just want to go to the last slide, we'll go ahead and share this deck with everyone. Or you already have it, but we're going to send it out with the recording. There are some resources here for you. You can try our developer edition immediately, and we have all the Graph Guru scripts on GitHub. And you can join our developer forum, and we have a new ebook too that we wanted to share with everyone as well. So we'll send links to everyone via email by the end of the day today. So we just wanted to thank you for taking time out today. We really appreciate it.
Thank you.
Thank you.